Great pleasure to be here, and a particular pleasure to follow on from your talk. So, in fact, I'm just going to say the same thing using different rhetoric. But there will be a challenge, mapping your rhetoric onto my rhetoric. I think that will be an entertaining game. Perhaps we can unpack that later. But everything you said makes perfect sense from the process theories that I'm going to be talking about. So my perspective will be, as intimated in the introduction, lower than his, but higher than hers, or perhaps the other way around. So I'm going to take a slightly more technical neuroscience process theory approach to implementing the sorts of ideas that we've just heard about. So I'm going to talk about predictive coding as a process theory that does all this, fitting the world to the mind and the mind to the world, with goals, putting constraints on that fitting. A process theory that could actually be done plausibly by neural networks, by our own brains. And I'm going to discuss it using the formalism of information theory and variational principles. These are just glorious terms for Hamilton's principle of least action. And that's where the challenge comes in mapping the rhetoric, but it can easily be mapped. So I'm going to split my talk into two 10-minute bits. The first will be just to review for you what people mean by predictive coding in its simplest or vanilla sense. And I should just preface this part of the talk by saying that normally when people talk about predictive coding, they're trying to predict what is happening now. So it's using internal explanations that provide the best prediction for the sensory impressions at hand now. And that's a slightly simpler problem than the reason that we're gathered here today, which is a much more prospective, what will happen in the future if I do this. And I think that distinction is very important, of course, speaks directly to the goal-directed nature of our behavior. So the whole purpose of this talk is, first of all, just to describe predictive coding vanilla, and then say how it could be generalized to embrace the challenges of making the behavior prospective and fit for purpose in relation to what we are trying to optimize. And I'm going to illustrate that using simulations of saccadic eye movement. So how do we sample? So the audience participation was a beautiful example of that, because I was only sampling information from the lowest buttons. And I'm going to try and simulate that using the principles that we've just heard about. So I normally start this talk just by acknowledging some of the key intellectual architects. I think most of what can be said that is of interest from the point of view of predictive coding conceptually was said by Hermann Helmholtz, beautifully articulated here with this phrase: objects are always imagined as being present in the field of vision as would have to be there in order to produce the same impression on the nervous mechanism. So what he's saying is, in order to see something, in order to fit your mind to the world, you have to have in mind an explanation or a model of what caused your sensory impressions. And that fits very comfortably with Richard Gregory's notion of perception as hypothesis testing. So the first bit of rhetoric mapping, learning equals perception in my talk. So we often talk about perceptual inference or perceptual learning. So when I talk about perception, I mean the learning, fitting the mind to the world. These ideas have been formalized by people like Peter Dayan and Geoffrey Hinton and many others in machine learning, borrowing from Bayesian probability theory, and indeed technical advances offered by Richard Feynman, variational principles that allow us to do approximate Bayesian inference. And I use that word now, or that phrase approximate Bayesian inference now, because of course if our inferences are always approximate, they are always false. So I love this idea of a good falsehood, because in my world everything is false. It's all approximate. And that approximateness comes from variational free energy formulations devised by in statistical physics. So those are the players. What then do they tell us about the notion of perception and action, or learning and action? Well, this phrase, the same impression, the sensory impressions, suggests that we are in the game of trying to explain the causes of the sensory impressions that fall upon our sensory epithelium, so our retina or our ears. So here we have some sensory impressions, and we'll denote them by S. So how might this notion of minimizing prediction error that we've heard about, how might this notion of optimization be invoked to give us some feel for how the brain would actually do this in a biophysical sense? And the example I'm going to use is predictive coding. It's also known as Kalman filtering or Bayesian filtering. It's also known as a minimization of variational free energy. It's just a variant of Hampel's principle of least action. Two twists or takes on the mathematical formalism. And I'm introducing them deliberately because one is a little bit high-flying, but it will be useful when we come back to the challenge that has been set up in the first talk. The other one is slightly more intuitive, cast in terms of prediction errors, and it's useful to explain, but they're both talking about exactly the same mechanism. So I've cast both descriptions mathematically here in terms of a flow of things called expectations about the world, expected causes of the world, that is either doing a gradient descent on free energy, variational free energy from Richard Feynman, that can be mathematically written down in a totally equivalent way in terms of predictions and updates. So what do these terms mean? Well, the prediction is this: if I have some expectations about the current state of the world, then I have some beliefs about what will happen next. If I had available to me the mistake or the mismatch or the prediction error afforded by a sensory sample from that world, then I can make a little correction to improve that expectation. So let me unpack that a little bit more intuitively. Let's say we were given this sensory impression, this shadow here of presumably some form of canine. If I wanted to explain that, I could have an expectation denoted by mu that if this was the cause of these sensory impressions, and if I had a generative model, a model mapping from this expectation or belief to the sensory consequences of this expectation or cause, I could simply create a prediction of my sensory input, G of my expectation, a generation of the prediction, and subtract it from the actual sensory input to obtain a prediction error. So the prediction error is just a mismatch between what I'm actually sampling and what I thought I was sampling, given I had some expectations about the state of the world. All that this equation says is that everything that can change will change to minimize the sum-squared prediction error weighted by their precision, so that we can explain all of brain function simply by minimizing prediction error. Now, again, this nice notion of falsehoods speaks to the fact we don't necessarily need to know what the truth is. All we need to do is to minimize the prediction error, and that is perfectly good. If I live my entire life with a minimal prediction error, then I will be well happy. I don't need to know the truth. That is nice because, as we've already seen, it accounts for the reciprocal directions of fit between mind and world. If we just have to minimize prediction error, we can do that in one of two ways. We can either change our internal brain states, our synaptic activity, our connectivity, that encode those expectations to make our predictions more like the sensations that we sample. Conversely, we can change the sensations by actively sampling them again, either through visual palpation or placing ourselves in a particular relationship to the world, so that we can change the sensory samples to make them more like our predictions. In both cases, we are minimizing prediction error just by changing either side of the equation. We're conforming to this imperative to minimize the sum-squared prediction error or variational free energy. And of course, from my point of view, that would be the rhetoric of action and perception, fitting learning and action, or fitting the mind to the world or the world to the mind at many, many different levels, but all happily subsumed under one simple principle. But if I have predictions, or if I want to elaborate a prediction error, then I have to have predictions and I have to have a model of how my sensations were caused. And of course, for us, those models have to be very deep, hierarchically structured, they have to be very dynamic, extremely nonlinear, high dimensional. So I've just cartooned what we get from that predictive coding equation in terms of an understanding of neuroanatomy and physiology in the real brain. Because if it is the case that the brain uses a model to generate predictions of what it should be seeing at this point in time, then the anatomy of the brain should entail and embody that model and should similarly have the same sort of hierarchical, nonlinear, and dynamical structure. So let's just think about the nature of these models. This is actually a graphical model, which some of you will be very familiar with, that contains hidden states and causes that cascade down to generate sensory impressions right at the bottom here, all subject to random fluctuations or uncertainty. A more intuitive version is here. So imagine I asked you to generate some synthetic data that reproduced foveal samples from the retina for your students, for example. How would you do that? Well, the first thing that you would have to do in generating these synthetic data would be to work out what is producing the sensory samples and where you are sampling. You'd have to work out all the kinetics and motion, oculomotor dynamics that sample this object, and equipped with this what and where causes, you would then be able to mix them together in a deep cascade, non-linearly, to actually generate a time series of sensory samples here. So the generative model maps from causes to consequences, whereas fitting the mind to the world inverts that. It's literally Bayesian inversion. It's literally this predictive coding. It's trying to solve the problem of going from the available sensory samples back to what caused them. And of course, that's exactly what that predictive coding equation does. And when we actually look at the form of the equations and how they might be mapped onto real brains, then something very simple emerges. We retain this hierarchical structure, but instead of the random fluctuations entering at each level, they now take the role of prediction errors and start to ascend the hierarchy. So that as the top-down predictions are used to form a prediction error, the prediction errors are passed back up again to assist or revise or correct the expectations at the higher level. So basically, we have a descending stream of predictions in exactly the same way that you generate these synthetic data for your students, that are accompanied by a counter stream of ascending prediction errors that are correcting at each point. And this is very reminiscent of real brain hierarchies, where you have reciprocal coupling of backward and forward connections that are all in the game of suppressing activity, eliminating prediction errors at each and every level of the hierarchy, such that when that process has finished, given some new sensory samples, you have a minimal prediction error, a maximum a posteriori expectation of what caused your sensory input with multiple levels of abstraction. So that's the basic idea. Let me just rehearse that for you in the context, say, of sampling the world. Here's a little cartoon of a brain. Let's imagine we have some visual information coming into the retina here that is passed to the lateral geniculate body, and it is in receipt of predictions from, say, the visual cortex, and that forms a prediction error, and the prediction errors are passed forward to revise or update the expectations or the beliefs about the elemental causes of this visual input. And of course, these expectations are themselves being predicted by higher level expectations or beliefs, and so there's a high order prediction error that's passed forward to revise these expectations that themselves will be predicted, and so on to any arbitrary hierarchical depth. Now let's look at exactly the same story, but from the point of view of proprioceptive input from my eye muscles that tell me about the state of my effector organs that I deploy to actually sample the sensory information that I'm trying to fit. So I've cartooned that here in terms of proprioceptive input from the eye muscles that come to the brainstem here, and they are predicted by, say, descending predictions from the frontal eye fields, and we could have, and that they form a prediction error that could ascend to revise my beliefs about where I'm looking. But here's the clever thing. These prediction errors can suppress themselves directly by coupling back to the real world, by causing the muscles to contract until the proprioceptive signals match the top-down predictions. And all that I've just described is just a classical reflex arc. So I don't need to revise my beliefs, because my beliefs are actually fit for purpose, provided that my top-down predictions, my coronary discharge or my motor commands, are realized reflexively by, in this instance, oculomotor reflexes. So that's the fitting the world to the model in a very, very simple way. The world here is just the sensation of my effector organs. But notice these predictions, these self-fulfilling predictions, are deeply informed by a hierarchical synthesis from all modalities. So these are not just predictions about my eyes, but they are contextualized by the context, what I want from the world, and are informed by integrating in a Bayesian sense all the information that come from multiple modalities. So that's the basic structure that I'm going to use. I'm going to close now. Let me just quickly summarize. Biological agents minimize their surprise or prediction error, or their entropy. They minimize that by suppressing prediction error. That can be reduced either by changing predictions, namely perceptual learning, or by changing sensations through active sampling. This entails, or perception or predictive coding entails recurrent message passing to optimize the predictions, while action makes those predictions come true and therefore minimizes surprise or free energy. So what I want to do now is introduce one of my favorite equations, and I'll do it very gently. It takes us back to, now we're back in the high church of variational calculus and free energy. And I have to do this in order to speak to the notion of what do we want to do when we sample new information? What is our goal? I have to say, it sounds a little simple-minded, but it is, for me, the truth. The only goal is to minimize free energy. The preferences actually come into the free energy through prior beliefs or prior preferences. So we heard about goals, desires, and prior preferences. In my world, those are prior beliefs about the states that things like me should occupy. And therefore, if I minimize my surprise or my prediction errors, then I will implicitly end up in my preferred states. But there is another aspect to free energy which I want to explore with you at the moment, which is what we've already heard about, the epistemic part of it. So what I've done here is express free energy in its usual way in terms of an energy and an entropy. So free energy is usually an energy minus an entropy, where the energy is a sort of information theoretic energy that comprises the likelihood, the probability of some sensory samples given their causes, beliefs about how those causes were engendered, and prior beliefs about the controllable aspects of the hidden states of the world generating sensations look like the position of my eye. Crucially, these prior beliefs entail preferences or beliefs about what I will do. And here's I think the most important point that I wanted to communicate today. If it is the case that it is sufficient to minimize free energy, surprise, or prediction errors, then the only self-consistent belief that I have about my action will be that I will act to minimize my free energy, surprise, or prediction errors in the future. And I can write that down just by making the probability of my control states where I am looking at the present time, the expected free energy following an action. And if we unpack that, and I'm not going to do that here, we can actually decompose that into the prior preferences that we've already heard about, the goals. So we had to do the smaller numbers, you had to do the bigger numbers. That defines the hypothesis space, and we would believe ourselves in this instance that we will provide the correct answer. But there's another part here which I want to focus on, which is the epistemic value or the information gain. And put simply, this is a component of free energy which is all about reducing uncertainty. And basically, all that this reduces to is that if you believe that we act to minimize our expected free energy, what you're saying is we are only in the game of resolving uncertainty about our hypotheses or beliefs in the world. And I think that's really important because much of what you were I think, trying to convey was the way that we carve our world in terms of a hypothesis space has an enormous effect on what we do and how we resolve that uncertainty. So, the nice audience participation example here, we just had the hypothesis there was a minimum card and a load of other uninteresting cards. Whereas for you, there was a high card and a load of uninteresting cards. So both of our hypothesis space were a bipartition. And then you were very cheekily challenging the poor subjects. Well, in fact, there was a hypothesis space that comprised three things: high cards and low cards, and possibly intermediate cards. So I think it was a beautiful example of inducing a model space, a hypothesis space. All this is saying is everything we do is in the service of resolving uncertainty about those hypotheses on the table. That's basically, and I'll quickly illustrate that, how that, say, can drive saccadic eye movements in the last slide, or last couple of slides. So just an illustration of that, that will be familiar for those people dealing with active vision and salience, possibly also attention to a certain extent. We were talking about attention just before the start of this workshop. So let's say I had a hypothesis that my visual impressions, my samples, foveal samples, limited to this little portion of the screen here, denoted by the circle, were generated by this bust or this statue here. This epistemic value or information gain basically scores a reduction in uncertainty about that hypothesis if I sampled there. And I can actually compute that, it's not difficult, and I can compute it for every central location determined by where I'm looking, you here, and create a map of the epistemic value, information gain, or salience. And this map actually does look as if it is a sort of mathematical object that actually attracts saccadic eye movements here from the classic work of Yarbus. So let me just see if I can simulate this active palpation, this visual palpation of the world. I won't go into this, it's just the same sort of graphical model that we were using before, and then convert it into a predictive coding scheme. Here, I just want to show you the results. So in this example, it's the last slide now, the agent has a hypothesis space of just three things can cause its sensory impressions. There's a face out there, there's an upside down face, or there's a face on its side. So its hypothesis space is threefold, and what it has to do is to resolve ambiguity and decide what's causing its sensory input. So what it's doing at each point is working out the most salient or the parts of the visual field it should sample to resolve as much uncertainty as it can, or minimize its free energy, expected free energy, as potently as it can. And what this produces are a series of saccadic eye movements, shown here in terms of the complete sequence here, and here graphically in terms of the movement of this little dot. So here is where the agent is looking. These are the salience maps driving these prior beliefs that I will sample the world to minimize uncertainty or resolve uncertainty. Simulated EOG, what it actually samples. And here's the most important graph here. It shows the expectation of the true, normally orientated face relative to the beliefs about the two competing hypotheses, the sideways or the inverted face here. And what we can see here is that within saccadic eye movements and between them, there's a progressive reduction in the uncertainty or the 90% posterior confidence intervals of a rather saltatory sort. And of course, as it keeps on sampling, it confirms its hypothesis, it continues to resolve uncertainty, and it happily decides this is what I'm looking at. Of course, if it didn't, then it would try to explore different hypotheses. So I'm going to give the last word to Helmholtz. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, I'll thank the people whose ideas I've been talking about, and thank you for your attention. Thank you very much indeed.